This video is about walking over uneven ground in SteamVR. All adventure games need a maze of twisty little passages, and Endangered will be no different. Here we can see a section of cave tunnels which will make up this maze. There are a number of issues to deal with here. We need to prevent walking through walls, using the methods from my video number 4. We need to detect changes in the floor level of our virtual world and change the mapping of our real-world play area to our virtual world. We can see this by walking up a slope. We need to offer teleporting to those parts of the maze we can see, but not those parts we can't, because we don't want to give away the layout of the maze. Here we can see there is a corner, but not what lies beyond the corner. But if we teleport into the corner, we can see both directions from the corner. In this video, I'll show you how to achieve all of these effects. We're going to use the Mine asset from the Asset Store. I've already downloaded this, so let's import it into our program. Window, Package Manager, Mine, Import, Import. Also, I'm going to disable our Chris Taylor character for this demonstration. In the project pane, go to Mine, Models, Base. Drag Turn R into the hierarchy. Follow this with Ramp Up. This raises the floor by 4 meters. All these tunnel sections are 12 meters long, with the origin in the center. So to align this with the previous turn, I set the position to -12, 0, -6, with a Y rotation of -90. Add a second turn R at position -18, 4, -6, also with a Y rotation of -90. Add a second ramp up at position -24, 4, 6, with Y rotation 0. These 4 sections provide a sufficient environment to demonstrate everything shown in the introductory in-game video. But although we have our tunnel with corners and ramps, each tunnel section is complete. Floor, walls and ceiling are a single mesh, whereas we need to distinguish between floors, which we are allowed to walk on and teleport to, and other parts of the mesh, which we are not allowed to walk through. Basically, we need to take the mesh of each section and generate 2 sub-meshes, one for the floor and one for not the floor. Each of these tunnel sections is an FBX model, so I'm going to import them into Blender. File, Import, FBX, Ramp Up. You could edit them in Blender, but I find SketchUp easier to use, so I'll export to collada format and then import that to SketchUp. File, Export, Collada, Ramp Up. Note, I use SketchUp version 8.0.16846. I've had this for many years. It has the advantage it is free, including for commercial use. Although it is no longer available on the official SketchUp site, you can download it from oldversion.com. I also used the plugin UV Toolkit, primarily for copying textures between front and back face. This requires TT Library, and instructions to install these plugins can be found here. When you import the tunnel section into SketchUp, you can see the mesh, but it is shaded on one side only and transparent on the other. I find it easier to have both sides shaded, so the first thing I'll do is right-click, Explode, then I'll shade all of both sides the same colour. Now, what I need to do is mark some of the mesh as floor. This takes some time, so here is one I prepared earlier. I've flagged the floor by colouring it red. It is important to note that the cross-section at either end is identical, allowing multiple pieces to be chained together. The same must apply to the dividing line between floor and not floor. I achieved this by defining the transition between these as a horizontal line at a specific height. You can see here how one of the original mesh triangles has been split into two to achieve this split at the correct level. I've already formed this model into two groups, one each for floor and not floor. So now I can simply delete each and save the other. Note the need to explode before exporting. I'll use file names based on the original with the suffix B for bottom and T for top. Before I add the top and bottom meshes, I'm going to formalize the maze hierarchy. Let's create an empty game object called maze and zero its position. Then I'll create an empty child game object for each of the four sections, giving them names which form an index: 0, 1, 2, 3. And let's make the first turn R a child of 0. To this, we also want to add the top and bottom meshes we just created. As you can see, these seem to be rather large. This is due to SketchUp exporting units of inches, whereas Unity treats the units as meters. So I need to scale by 0.0254. Now, we don't want to see these, we only want them for collision purposes. So we remove the mesh renderer and add a mesh collider in each case. Now you can see we have discrete colliders for the floor, bottom, and not floor, top. To comply with the requirements of my video number 4, Don't Walk Through Walls in SteamVR, I need to add a child to the floor called Ignore Player Collision. This will allow us to walk on the floor, whilst the lack of this child on the top mesh will prevent us from walking through walls. Please refer back to video number 4 if you haven't already watched it. This will explain how these various collision meshes are used to control what you can walk on and can't walk through. We are also going to need to adjust for height above the floor, which means we need an easy way to identify any piece of floor. To do this, I am going to call all maze floor sections floor. Finally, we need to be able to teleport to a floor. We also need to be able to set these teleport targets active, true or false as necessary to only reveal the visible parts of the maze. So, we create another empty child called teleport and place another bottom section here. Once again, adjust the scale and then add a mesh collider and teleport area. If we look closely at this teleport area, you can see the mesh rendering interferes with that of the rock texture render. To get round this, I set the Y position to 0.1. Also, as this is another collider which forms a floor, this also needs a child called Ignore Player Collision. I'll duplicate this now complete turn R section to create the other turn R at index 2. Set position to -18, 4, -6 and Y rotation to 90. I also have to do the same thing with the two ramp sections. I'll skip this to avoid dragging out this video. You should end up with a structure like this. Now we add the script maze piece to each of the sections. This provides low and high index values for the maze pieces which can be seen. Piece 0 can see pieces 0, 1 and 2. Piece 1 can also see pieces 0, 1 and 2. Piece 2 can see all the pieces. Piece 3 can only see pieces 2 and 3. We also need to add the script uneven ground to the maze game object. And finally, before I run this, I'll disable the large plane that we created for video number 7 animation. OK, let's run it. Here I can look around in the mine tunnel. Now I'm going to demonstrate attempting to walk through the wall. As you can see, the wall moves away from me to prevent me walking through it. If I press the teleport button, you can see that teleport is possible to the corner, but you cannot see what is beyond the corner. I'm now going to teleport to the base of the slope, and I'll start walking up it. And if I turn round and walk down, you can see I'm descending the slope. If I teleport to the top corner, I can see round the corner, and looking in the other direction, I can see back to where I started. But if I go right to the top, I can only see back to the corner. And let me go back to the middle. And repeat walking up the slope. Let's examine the script. Maze piece is simple. It contains the piece-specific data, which in our example is limited to the lowest and highest piece numbers which can be seen from this piece. It would, of course, be possible to add any required piece-specific data. One example would be to record which part of the virtual world outside of the maze tunnels, if any, is currently visible. This could be used to set non-visible regions of the scene to inactive. Uneven ground handles the height adjust and setting teleport areas active or inactive as required. The start function caches the transforms of the VR camera and the play area. Also, for each of the maze pieces, it caches the maze piece component and teleport game object, initially setting all the teleport game objects to inactive. The update function initializes an invalid piece number, -1. This is used to indicate either we are not in a maze piece, or we can't identify which piece we are in. The play area position is checked against the previous value. If they differ, this suggests a teleport has just taken place, in which case we should omit filtering of height adjustment for this iteration, i.e. we want to snap to the correct height. Next, we initialize the real and virtual height, the virtual height currently being unknown. We determine the virtual height by emitting a ray vertically down from 10 cm below the VR camera position. This 10 cm offset is to avoid the ray colliding with the VR camera itself. If we hit something, and if that something is called floor, then the hit distance is the virtual height of the VR camera above the floor, remembering to add back in the 10 cm offset. The parent of this floor game object has a name of the form 0, 1, 2, or 3. So, whilst we are here, we extract this to obtain the piece number. Next, we limit both real and virtual heights to the nearest centimetre. This avoids continual adjustments by insignificant amounts. We only consider adjusting the height if the real height is at least 0.6 meters. This ensures the headset is not simply resting on the floor, but does allow for use by children. Also, we must have derived a valid virtual height. Finally, we ignore adjustments less than 2 centimeters, i.e., we only adjust if really necessary, as if adjustments occurred too frequently, this could lead to motion sickness. By experimentation, I found 2 centimeters was a good compromise value. Unless the filter is to be omitted, the magnitude of the height adjustment is reduced to filter over approximately half a second. This new play area position is then applied. The last action of the update function is to call process maze position. This separates those actions which are piece-specific from the height adjustment. Process maze position is used to inspect the maze piece data. In our example, which other maze pieces are visible? Initially, it is assumed none are visible. If the past piece number is valid, the piece data is used to flag which other pieces are visible. Then, any maze pieces whose visibility has changed are set active or inactive as appropriate. My next video will look at applying the principles from this video to terrain.